In this presentation, I will present our CVPR Highlight paper titled Geometrically-driven Aggregation for Zero-Shot 3D Point Cloud Understanding, co-authored by Guofeng, Luigi, Yiming, and Fabio. Let's first take a look at current methods for zero-shot point cloud understanding. Typically, they obtain point-level features by aggregating their corresponding multi-view images, or by distilling a 3D encoder from image-based VLM representations. Well, with these methods, we observe a few limitations. First, the VLM features extracted from multi-view images, although they are rich in semantics, the spatial and geometric information anchored to the point clouds are usually lost. Then, current way of injecting geometry into point representation, for example, by distillation, requires extra training. Finally, as the camera calibration is not accurate all the time, the 3D reconstructed point clouds can be also noisy. Therefore, the eventual 3D semantic segmentation results are noisy. To address these limitations, we propose GeoZe, the first training-free geometrically driven representation method for zero-shot 3D point cloud understanding. By aggregating VLM features with both local and global spatial information, we can reduce noise in the point-level representation, achieving better semantic segmentation performance. We believe that the geometric structure of a point cloud contains valuable information that could be used to enhance the quality of the transferred VLM representations. So the key idea behind our proposed solution is that VLM representations should exhibit local smoothness and global consistency when their geometric structures are similar. Now, let's dive into our proposed method, GeoZe. We begin by extracting dense pixel-level VLM representations with clip from each viewpoint of the point cloud. These representations are then projected onto the 3D points. For the point cloud, we compute the geometric representations using fast point feature histogram to guide the VLM aggregation. By utilizing point cloud coordinates and geometric representations, we can further generate superpoints along with their associated geometric and VLM representations. For each superpoint, we identify its k nearest neighbors within the point cloud to form a patch. For each patch, we perform a local feature aggregation to denoise the VLM representations. Then, superpoints undergo a process of global aggregation. Specifically, we apply mean-shift clustering on point-level VLM representations to establish VLM representation anchors. A global-to-local aggregation process is further applied to update the point representations based on the coordinate distance and VLM representation similarity between points and superpoints. Finally, we employ the VLM representation anchors to further refine point-level representation, which become then ready to be utilized for any downstream tasks. We provide visualizations for each step of the GeoZe process. As we can see, the extracted VLM features, when projected to the point cloud, contain noise, as highlighted in the red boxes. By applying local aggregation, we can effectively eliminate such noise in the red box regions. Subsequently, global aggregation further smoothens the semantic representation in local regions by accounting for consistency among neighboring regions. Finally, with the superpoint-to-point aggregation, based on the relationships between superpoints and points, we can obtain an improved segmentation output. We report the results for zero-shot object classification on ModelNet 40 and ScanObject.nn. GeoZe surpasses PointClip v2 across all datasets. We also show the t-SNE comparison of the class representations extracted using PointClip v2 and GeoZe. GeoZe produces better separated and grouped clusters for different categories. Moreover, GeoZe also scores the new state-of-art performance on both indoor and outdoor semantic scene segmentation tasks on ScanNet and NewScenes. The segmented regions are more homogeneous with reduced noise, particularly at the point cloud boundaries. Please check our project page for more information. Thanks for listening.